Hi everyone, welcome to the introductory Python tutorials with a focus on image processing related tasks. In the last couple of videos, we looked at classification tasks. In fact, in the last video, we looked at multi-class classification, and the next one in the line would be multi-label classification, but there aren't many examples when it comes to microscopy, so let's skip that for now. So the next one after that would be semantic segmentation, where we are going to segment every pixel or classify every pixel. Now, this is a very, very common task when it comes to microscopy or scientific imaging in general. Now, to understand semantic segmentation, I thought you need to know what autoencoders are first, and then relate autoencoders to semantic segmentation. So in this video, I'm going to talk about autoencoders, and then in the next video, let's extend the knowledge of autoencoders and see why we need a different approach, or not completely different, but a related approach, but a modified approach, I should say, for semantic segmentation, okay, where we are going to segment every pixel. But first, let's understand autoencoders, because this is another topic that you will see or you will hear about when you're trying to learn deep learning topics. So let's jump in. First of all, if you look at a deep learning classifier, okay, we have used this, right? I mean, we have used a similar structure in our previous videos. So this is an example of VGG16. I'll talk about existing famous, architectures in one of the upcoming tutorials. But VGG16 is an architecture that won an award 5-6 years ago on the ImageNet challenge, where you had to classify 1,000 different classes. Okay, you have to classify images that could fall into 1,000 different classes. So this is an architecture. Again, let's not spend too much time understanding exactly what the architecture is, why it is designed, how it is designed. But the reason I'm showing this is, for any classification task, or in most of the deep learning tasks, you have convolutional layers and you have dense layers, right? The convolutional layers are there to generate features from your images. If it is structured data, if you already have a CSV file where you have, for example, for our breast cancer data set, we already have like area, radius, and other measurements, right? So these are all attributes. These are all features that already came with it. Now we can do feature engineering on top of that by combining these features together. When it comes to images, what are features? Well, you can apply Gaussian filter, you can apply edge detection filters, and you can generate your own features. But we don't know whether those are the right features that describe the image or the objects that we're trying to segment in our images, right? So that's why we approach deep learning, where these features can be trained, meaning we can train a model to understand those features. Now, let me explain that a bit further. So these are all convolutional layers. What's a convolution? Again, this is like Gaussian filtering. You have a kernel with some specific numbers in it, and you're multiplying those numbers with the pixel values in your image. This is a convolution operation, right? So you have various different convolutional layers in a convolutional, based deep learning architecture, let's say. And then we are adding a bunch of dense layers. So the job of these convolutional layers is to learn what the best features are at that level to describe the features of your interest. So here the image is pretty large. You see 224 by 224, and you have 64 such filters, meaning you see there is some thickness to this. That thickness is 64. That means you have 64 images for every image that you feed in. So one cat image or one mitochondria image, you have 64 of those mitochondria images, but they're all filtered using these 64 different filters. And then comes 128 filters and 256 filters. The number of filters keep increasing as you go towards the right. At some point, your image size is small and you have lots of filters like 512. Why is the image size going down? This is again something, I'm not talking about autoencoders at all. I'm talking about the basic construction of your convolutional network that you probably know, but can benefit from this reinforced information. So we start off in this example with an image that's 224 by 224, right? And then you apply some sort of a max pooling operation. You see the red box right there, that represents max pooling, meaning you're not taking all the pixels from here to the next level, you're pooling it. In this case, you're using the maximum pooling, meaning if I apply a 2x2, meaning 2x2 kernel, what is the maximum value within that kernel, and then take that. That means my image size gets already half when I go from here to here, and then half here, and then half here. That's because my max pooling size is 2x2. That's it. Okay. I think this is all the information you know anyhow, but this is just an extension of that. So why am I showing this? Because at the end, your large image, which was 224 by 224 pixels, now is only represented by 7 by 7 pixels. That's it. Except you have 512 features, right? So it's a small vector, but then you have mini features right there. And then you feed that, you flatten this, meaning you take 7 multiplied by 7 multiplied by 512, which looks like it's 4096. How many ever that features, they go into this dense neural network with an output of 1000. So you can predict one of 1000 classes. That's it. And then you train this. Okay. Now, this is a regular convolutional network. Okay. If you feed in an image, for example, Einstein image in this case, and you train the model on a whole bunch of Einsteins and other images, and your output would be a prediction saying, okay, this is Einstein with a probability of, I don't know, 90+%, and this is someone else with a probability of whatever that probability is. And then you say, okay, my prediction is Einstein, right? So this is exactly what we have done in our multi-class classification in the last video. Now I'm just explaining different convolution layers and the dense layers. Okay. Now let's take this architecture, and then instead of the dense layers, what if I replace that dense layers with something else? Okay. Now, why would I want to do that? Because if you look at this, why do we have these many convolution layers? After the first convolution layer, you see the type of information it learns from the images. And after the second convolution layer, you see a different type of information that it's learning, like it's learning about roundedness, right? Different textures and so on right here. And as you go deeper and deeper, the features get richer and richer. Like you see, you have 512 of these features as you go deep in here, but this is an example from layer number 3. So as you go deeper, this is why deep neural networks are amazing, because you're mapping different at different levels, you're mapping your features in your image, yeah, with a specific convolutional layer. So here you're getting some information, and then as you go deeper and deeper, they get very abstract. Now you can't even tell. I mean, here you can kind of tell that, oh, this is actually detecting edges, you see, right there. So around here, layer 3, it's detecting some edges. But here I see some sort of a roundedness and other features. But let's not worry about what exactly is detecting at what level. That's a different science altogether. You can dig into that, and it is fun, believe me. But for now, let's understand that at every level there is a different feature, and our representation, gets richer and richer in the feature space as we go from left to the right. Now let's think about, okay, we have this architecture. Now I would like, my task in this case is not classification, but autoencoding. What does that mean? First, let's replace the classification part with exactly the left-hand side, except mirror opposite. So if I go back, this is our classification. All I'm doing is take the dense layers out, because my focus is not in classifying the image, but my focus is on reconstructing the image. So if I go back, what if we take exactly the same stuff and then put it in a mirror opposite? Meaning from this point, it's going up in the size, like from 7 by 7, it's going to 14 by 14, 28 by 28, and then 56 by 56, 112, and then finally you have 224 by 224. And then the number of features are going down. So all we're doing is just building something that's opposite. This is the structure of an autoencoder. This part, where you go from a large image all the way to a small vector, is called the encoder part, and this part is the decoder part. Now, there are many applications, we'll talk about that, but why would anyone want to do this, right? I mean, first of all, what does it do? Well, you supply an Einstein image as an input, it reconstructs an Einstein image. What good is that if it does exactly the same thing? There are many applications. One, you can think of, you want to compress this image into a very small vector, like then you can just take this image, compress that into a small vector, then just ship the small vector. And then if the other side, if they have a decoder, meaning how to take this image and decode it back to original image, there you go. Then you have an efficient way of transferring data, right? Because they already have a decoder and you already trained this model, and all you need to do is just encode an image and send it. Right, that's just one example. I'll talk about a couple more in a minute. But this is basically an autoencoder. You have an encoder path and you have a decoder path where you're reconstructing the original image back. This is fun to do, by the way. And there are many tricks you can do. You can trick this system by saying, hey, my input image is not this, but something else. I'll talk about that in a minute. But how do you construct this? How do you write code for this? And this is very simple. Remember, when you're putting this together, you're going down. All you need to do is go back up. I'm just showing a couple of lines. When you're going down, you're using convolutional operations, right? How many filters? 8 filters. And what is the size of the kernel? 3 by 3, and activation and so on. This part I hope you know if you watched my previous videos. And then we are adding max pooling, the red layer right there, right? 2 by 2. What does max pooling do? It brings your image size by half if you are using 2 by 2 max pooling. Yeah, so it goes from this to that. What do we do when we are doing the opposite journey from here in the decoder? So we add our convolutional layer right there, okay? But then when you do, the next step would be upsampling. So think of upsampling as opposite of max pooling. So in max pooling, you're doing a 2 by 2 max pooling, and then the image goes down. And I'll talk about upsampling and conv2D in the next video, by the way. So you know more about what upsampling is. But think of upsampling is just taking your smaller image and then copying the pixels and doubling it. If your image is 1, 2, 3, 4, think of the doubled image as 1, 1, 2, 2, 3, 3, 4, 4. Now your image is 2 times the size, right? Something of that similar, of that sort. So we are going to use upsampling or convolutional 2D transpose. So there are ways to go up. And not just down here. So that's exactly what we are going to use. Once you do that, when you fit model.fit, normally when you model.fit, it's X and Y. You're training X train and Y train, right? So Y is what you're trying to predict. But in an autoencoder, what are you trying to predict? Your original image itself. So in autoencoder, your X equals to your Y. So X and X, this is how you train it. Okay, and by the way, one other note here, if you have, for example, thousands of some type of images, let's say thousands of electron microscopy images that shows mitochondria and a whole bunch, but then you don't have any annotations. Yeah, one way you can kind of benefit from that data set, if someone is giving you that type of data set, is by creating an autoencoder and training all the data set on autoencoder and taking only the encoder part, the left-hand side, and using that as your feature extractor. Now you can just take the left-hand side. You have already trained that on your images, so it knows what roundedness looks like, what textures it needs to expect and everything. So all you need to do is take the left-hand side and add your dense layers and a classifier, and then you can classify it. Obviously, you need some training data, annotated data, but just thinking out loud some of the applications here, okay? So now, let's look at some applications of autoencoders. You can use it for denoising, although this is not a very efficient way of denoising your images. Let me say, it's fun, it works, but for large images, this can be very difficult. Yeah. So the way you kind of convert this into a denoising autoencoder, I definitely encourage you to try this, is by supplying your X. Remember, if I go back, X and X, you can trick an autoencoder by giving X and then instead of X, give Y, meaning something else. So for example, if my X is noisy Mona Lisa image, and if my Y is a clean Mona Lisa image, you will train the network to learn on noisy, but then give a denoised output. I hope that makes sense. Another example is you have a bunch of data that looks one way. Yeah, it can be image data also. you have a bunch of images that look one way, but then think of semiconductors, right? You take images of these semiconductors and then you don't want any contamination on it. So you train the algorithm you train autoencoder on all of these images, but then when you have a contamination on it, what happens? The image, this autoencoder, all it knows is to reconstruct your original image. So it does reconstruct this original image, but then the final reconstructed image will have the missing contaminant. Why does that even matter? Well, when you look at the reconstruction error, meaning when you compare your original image and the final image and reconstructed image, and you get a reconstruction error, on images that have anomalies, the reconstruction error would be high. Same with any other data. Okay, you have some data that looks away, and then when you reconstruct it, when some data that has anomaly, when you reconstruct it, then it shows you that, hey, I did reconstruct, but the reconstruction error right now, when I'm training it, when I'm predicting it, is pretty high, right? So that's how you can use this architecture for anomaly detection. Okay, another application there. Image colorization is something also fun to do. You again provide a bunch of black and white grayscale images as X as your input, and equivalent color images as output, and then train the model. And in future, when you supply a grayscale image, it colorizes it. This works pretty nicely, actually. So although I should say for larger images, this can be computing intensive, but for small images, this like 256 or smaller, this can be a very fun exercise to do. Please go ahead and do that. And finally, our goal is semantic segmentation. We're talking about autoencoders in the context of semantic segmentation. Okay, so can autoencoders be used for semantic segmentation, right? I mean, here we are tricking them by giving some X. All autoencoders knows, is to reconstruct the original image into something that we used as our Y, right? So what if I train this autoencoder on a whole bunch of images and equivalent masks or segmented images? Can I actually build an autoencoder that can perform semantic segmentation? That remains to be seen. So you have to watch the next video and the one after that to figure out if that's an easy, if that can be used. If not, why? Learn why, and then fix that why, right? There must be a reason why it's not ideal. Then how do we fix that, and how can we get to the semantic segmentation? But before doing that, let's jump into the code to do a fun exercise of loading an image and reconstructing that using autoencoders, okay? So I'll share the code again as usual, so please focus on what I'm trying to convey here, okay? So let's go ahead and import some libraries. These are pretty much standard, like matplotlib, pyplot, numpy, opencv, and then I'm loading image to array. We'll see if I'm using it. And to construct our model, I'm going to use convolutional 2D here, and I'm going to use max pooling and upsampling, right? These three layers, and then sequential method is what we're going to use to build our model, and model is where what we use to kind of construct our model. So let's go ahead and run these lines. And I'm defining a size of 256 just to make sure that my input image is resized to that specific size. That's it. And I'm reading a Mona Lisa image that I downloaded from the web. And nothing to share. I can't share this. I don't own this image, but I'm using it for demonstration purposes. So I downloaded that and I placed it in my Google Drive right there. And that's the link I'm using right here. Okay. And since I'm using OpenCV, I'm converting my image from BGR to RGB. Again, remember, in OpenCV, your image is read as BGR, not RGB. So why am I changing this? Because when I plot it, it looks in natural colors rather than inverted colors, right? And I'm resizing it and go ahead and print out the shape. So hopefully it should say 256, 256.3. It's a color image. 256, 256 is the size. Okay. Now let's go ahead and expand the dimensions. So this is typical input to our neural network, right? So number of images and the dimensions of the image. So we have only one image. So let's go ahead and do that. Now let's divide our image pixels by 255 because this is a grayscale image. Okay. So we are just scaling my image. Now here is the autoencoder part. Yeah. I'm using sequential method and I started off with 64 filters, 128 filters, 256 filters. And then going back down, 256, 128, 64 with a final output of 3. Why 3? Because this is an RGB image, so I have 3 channels. So 3 would be the output, yeah? And I'm max pooling, and everything else should be pretty much the same. This is no different than your classification from last video, except in classification, after this part, after the max pooling part, we added dense layers and an output. That's it. And here we are just copying exactly the same, except we are doing upsampling after convolution, upsampling right there. Okay, so that's our, let's go ahead and print out the summary so you can see exactly how this looks like. And this is, autoencoder doesn't have a specific shape. You can do anything. You can add your batch normalization layers, you can do mask pooling. The idea, the concept is it goes down in size and goes up in number of features, and then exactly opposite in the decoder path. As long as you do that, you can design your own autoencoder. Okay, there you go. So going from 256 to 5664 to 128 to 64, all the way down to 32 by 32 by 256, and symmetrically opposite all the way up to 256 to 256.3. There you go. And I have 1.3 million parameters to be trained, but this is a small image. So let's go ahead and fit it. How do we fit an autoencoder? Well, my X is image array, my Y is image array. Both are the same. Yeah, so X and Y. And how many epochs? 1000. Well, it may sound like a lot, but once this starts, it's pretty quick. Okay, this goes by pretty fast. So you'll see that in a second. I'll probably pause the video even though it just takes a few seconds to complete these 1000 epochs, but I just want to make sure you get a quick glimpse at how this is progressing. I just initiated this runtime, so it takes a few seconds, as you probably know, to get the GPU and everything ready. And once it goes, it should be there you go. Even before we realize it's pretty fast. Already 200 or so. So let me go ahead and pause this. I'll continue the video as soon as this is done, which is a few seconds. Okay, so there you go. It's done, and looks like the accuracy that we are getting is 92.9, like about 93% accuracy. So what does that mean? Let's go ahead and predict on our original image that we supplied. So if you print, oh yeah, it did the prediction, but we need to plot it. So let's go ahead and plot it. And there you go. That's the original, and that's the reconstructed. That looks very close. I mean, you see it's a bit blurred. If I kind of give this a few more epochs, or even design my autoencoder in a nice, better way, so I get even more features, then this may look a bit more close to the original. But you see how a little blurred the entire image is. Again, that's coming from the fact that we lose spatial resolution as we go down, but we have feature information, and we regain spatial information in a way when we are coming back up. So usually the reconstructed image is slightly blur compared to the original, but then you can also try upscaling instead of upsampling using convolutional 2D transpose and see if that affects this. Again, that's a fun exercise. I'll leave that to you. Okay, I think this is enough about autoencoders, and in the next tutorial, let's continue these discussions eventually with the goal of understanding semantic segmentation. So let's meet again in the next video.